Could you tell me? Could you tell me what does the curve of stress and strain discuss about? Explain it. If you know, okay. If you don't know, I am going to explain it. Graph of curve means graph of stress and strain. We know that if a graph of stress and strain is providing constant, a linear line, it means Hooke's law is being followed. Okay, followed. Let me draw a figure. This is our stage and strain. Its origin. This A point, B point, C point, D point, E. Look, it will provide some terms. Some terms. This graph will be providing some terms. First of all, let's read PPT. When a wire is being stretched, means somebody is stretching a wire by a load. Load means force. By force, we are applying. We are stretching a wire. It is seen that it is observed that for a small value of load, amount of forces are small. For this extension produced in the wire is proportional to the load. Mean stress is proportional, directly proportional to strain. If amount of the forces are small, then change in length will be small. If amount of the force is more, change in length will be more. This is what makes meaning of directly inversely proportional. Okay. On removing the load, when load or force is removed, the wire returns back its original length. All these things we know, but you can say this is a what repetition. When load or deforming force is removed completely, then what happens? The rod wants to gain its original shape or its configuration. Original length. The wire regains its original dimensions only when the load applied is less or it's equal to a certain limit. But remember, stress will be equal to stress will be directly proportional to strain when we are in elastic limit. If we cross elastic limit, then what will happen? That material will not be elastic. Instead, it will become plastic. Okay. This limit is called elastic limit. Yeah. So this phenomena where stress is becoming directly proportional to strain. So this phenomena happens in within elastic limit, within a limit. So this phenomena is known as elastic limit. Okay, so I think you have understood about elastic limit. Elastic limit, this thing is clear. This is nothing but it is the limit of a force, we can say. If we apply more than requirement force, then of course body will not regain its original shape. Okay. Thus, the elastic limit is the maximum stress or on whose removal. Removal. So this is nothing but it is a maximum stress, maximum stress, or you can say maximum force, maximum deforming force. This is nothing but maximum deforming force on whose removal. The bodies regain their original dimension in shown figure. In this figure, the type of a behavior is represented by OA. Where is OA? This OA. OA. Portion of the graph. Till A, this stress is this till A. Stress is proportional to till A. Okay. Till A. Stress is direct from 0 to A till from 0 to A. You can say stress is directly proportional to stress. Okay. It means this is a straight line. Constant. Okay. Okay. But after this A, you are not going to get a same directly proportional to stress. Straight directly proportional to stress. No, this is not happening. It means after A, it is not flowing what? Hooke's law. After A, does not flow. And okay, next strain and stress from A to B. If a deforming force are removed, means if we remove this stress, then what will happen? I remove, then wire comes to its original length. But here stress is not proportional to strain. Here you can see till over here. Over here, if you remove a deforming force, then what will happen? This will come to 0. This will come to 0. But when it goes over here, what is happening? Still it is increasing. Stress is increasing, strain is also increasing. But after this A to D, this is not constant. Means stress is not becoming to strain. For example, strain is at 7. So over here, the strain will be something else. I think it should be 9 or 7, but not exact same. 7 to 7. 7 to 7. Now let's see all these parts. O to A we know. O to A is a constant. Means Hooke's law is present over here. Okay. Next, OB. This OB. OB is elastic limit. Means till here, till B, here stress is maximum. Try to understand. till here, stress is maximum. If we cross this B, then what will happen? Either it will break or it will become plastic. Either it will break or it will become plastic. Am I correct? So till the B, this is showing that it's a elastic limit. Okay, it's elastic limit. Okay. C is what? C is yield point. Yield point. This C is a yield point. What is yield point? We will discuss about it. Don't worry. And CD is nothing but CD. This is CD. It is talking about this is CD. CD is nothing but it is a plastic behavior. Plastic behavior. Here you will see exact behavior of a plastic. Means it will not regain its configuration. Where C to D, C to D. Till the B, this was elastic limit, but after this you will see that it is becoming plastic behavior. Okay, but when we cross plastic behavior, then what will happen? It will break. Body will break. Means stress is constant. Stress is constant, but strain is increasing. Strain is increasing, or you can say strain is decreasing. Clear? Study was plastic behavior. D is the ultimate point, and DE is a fracture, or you can say breaking stress, breaking point. Over here, between this, our body will break because it reached till the it crossed. I think we should say it crossed limit. That's why body will break itself. Now let's explore more about it, so that our understanding related to this can become more clear. As we go beyond the point B, ahead of this, we now till B, it is showing elastic limit of the body. It is showing elastic limit of the body till B. But what will happen when we will go beyond B? Beyond the point B as shown above, then even for a very small increase in stress, a small increase can be seen in stress even after B, very small. Then stress produced is very large, but strain is very large. Means length, or you can say volume is changing. After B, either length will be changing or volume will be changing, but force is the same. Deforming force is the same. If length is changing, or volume, at a point, of course, obviously at a point will come where the object will become more thin, and then it will break itself because of due to increasing length of the body or volume of the body, but length of the body. Are you understanding? Only strain is increasing. Try to understand. If the stress is fixed and strain is decreasing, if stress is fixed but strain is increasing, what will happen? At a point, body will break itself, at a point. That point will come where it will break itself. Okay. This type of behavior is observed around point C. Where is point C? This. Around this, what kind of behavior? So here only strain is increasing, but strain is fixed. This type of behavior can be observed around the sea, and at this stage, the wire begins to follow like a viscous fluid. Means it is just it is, since we know strain is increasing, means thickness of the body is becoming thinner, or you can say thickness of the body is decreasing like a fluid. Okay, like a fluid. The point C is called yield point. This point is nothing but yield point. So over here, so try to understand what is yield point. It is telling you that after this or around this point, strain is increasing. Yield is nothing but this is our yield. You can say yield point. Yield point is a point where strain stress is fixed but strain is increasing. Means thickness of the body is decreasing and length of the body is increasing. This is what is meaning of a yield point. If the stress is then further increased, what if we only increase stress? Okay, stress. We are going to increase this stress. Then wire breaks off at a point D. Where? Over here. Over here, it is the wire will break itself at D point. At D point. So D point called the breaking point. D point we are calling it as a breaking point. The stress which is corresponding to this point is called breaking stress or tangential strength of the material of the wire. The material for which the plastic range CD. Where is CD? This CD is a range of a plastic. Remember, from here to till here, this is what is the range of elastic limit. Elasticity you can say. From B to D, you can say this is our plastic range. The material for which the plastic range CD is relatively high is called ductile material. Ductile material for which the plastic range CD is a ductile material. Ductile material DUCTIL, ductile material. Try to understand. If when you will increase limit of plastic behavior, then what will happen? when when you cross limit of plastic behavior, then what will happen? We will get a breaking point. That is known. This phenomena is known as ductile. Ductile. The materials for which the plastic range is relatively small are called brittle materials. These materials break as soon as the elastic limit is crossed. If you don't, if you didn't understand, don't worry. Again and again, they will understand. So important points. We have some important points for this. Important points. First, breaking stress. Breaking. Breaking stress is nothing but uh, breaking stress is nothing but breaking force. Breaking force upon area. Upon area. Okay. Second point. If you are calculating breaking stress, then formula is the same as we use for stress. Second point is the breaking stress is a constant for a material. This is also constant. Okay, the breaking stress is constant. Here we see that stress is fixed, means constant, but strain is changing. That's why breaking stress will be breaking stress is a constant. But when it comes to what? I think strain, breaking strain, then we will say strain is increasing. Next point, breaking force depends upon the area of the section of the wire of a given material. Yeah, of course. If there is no area, then where will you apply force? So yes, breaking force will be depend on area of that body. Next point is the working stress is also always kept lower than that of a breaking stress, so that ignore this statement, this one. Next part is breaking strain. Breaking strain is equal to elongation or compression. Compression means compressing the object. Elongation means stretching the object. Okay, upon original dimension. This are about breaking stress, but now what about breaking strain? So breaking strain is nothing but this is equal to elongation or compression upon what? Upon original dimension. Original dimension. Okay, now next point. How much length was pulled or pushed? Just put in millimeter. And what was original dimension of that body? Just put in millimeter. You will get breaking strain. This breaking strain is not equal to breaking stress. Change in dimension upon change in change in dimension upon original dimension. This is nothing but same thing. Change in just we wrote in more details. It as a details. instead of a change in length. Instead of a change in length. Now next topic, which is elastic after effect. Elastic after effect. Elastic after effect. Try to understand what is this word saying. There is elastic, but elastic after effect. After effect, what is elastic? Let's read PPT. We know that some material bodies take some time in order to regain their original configuration. There are some bodies when force deformation force is applied and then we remove, what happens? They take, those body take time, little bit, but yes, they take time. Why they take time? They take time to regain its configuration, and this little bit timing which is being taken by the object to gain its configuration is our elastic after effect. Okay, when the deforming force is being removed, the delay, or you can say delay in the regaining of original configuration by the bodies on the removal of deforming force is called elastic after the effect. Just I said, the little bit of time which is being taken by the object to gain its configuration is our elastic after effect. Or in other words, you can say the delay of regaining its configuration on removal deforming force is known as elastic after effect. Elastic after effect. Let me write it on this board. So definition for elastic. Elastic after effect is nothing but the delay. Okay, the delay in the regaining of original configuration by the bodies on the removal of deforming force is called elastic after effect. Elastic after effect. This was a definition of, this was the meaning of elastic after effect, nothing else. Let's see more about it. More sentence about it. The elastic after the effect is negligibly a small for quartz fiber. Quartz fiber is also it is an object. So for this object, this delay time is negligible. They will neglect time for that object which is a quartz fiber. And phosphor bronze. bronze. For this reason, the suspension are made up of quartz and phosphorus. Okay, I got this sentence. Just uh, keep this in your mind, or you can understand this. What is it saying? For glass, fabric loss is after effect is very large. Is very large. It is saying that glass has a very large elastic after effect. Very large. It takes hours of a glass fiber to return to its original state or removal on removal of deforming force. Of course, they will take. But when it comes to flexible object. So flexible object, I think they will take less time to regain its original state. So in that case, we can say that flexible object has a less elastic after effect. But when it comes to iron, glass, they have more large elastic after effect. Means they will take time more to regain its original shape. For example, this marker is it has also a large elastic after effect. When we will apply deforming force on this object and it just remove this deforming force, then what will happen? It will take time to regain its original shape. Means time is more, so we can say elastic after effect is more. If time is less, you can say elastic after effect is less. Okay. Next topic you can say elastic fatigue, 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 elastic fatigue. This is also new word. It's a completely new word. But only fatigue is a new word, not elastic. Not elastic. Are you understanding? Not elastic. What is it saying? The loss of the strength of the material due to repeated strains. Wow, this is very important. Not important, but interesting point, because it is seen in our nature, in our world. I will tell you some examples of elastic fatigue. The loss of the strength of the material, um, or you can say the loss of regaining original shape of the body, is what is our elastic fatigue. And it happens when uh, deforming force is being applied many times, and object is applying restoring force many times, then we get elastic fatigue. And that's why it is advised that change that object, otherwise it will provide unsafety. For safety, just change that object. And examples are uh, shocker that are present in cycle or in a vehicle. We see that like this. So here, deforming force, restoring force, deforming force, restoring force. You can see it is repeating with respect to time. So one time will come when it will tell you I am done. It is happening because of repetition of deforming force and restoring force. So you can say it is nothing but repetition of deforming force and restoring force. Restoring force. Restoring force. Due to it loses its configuration, or you can say original shape. Configuration or original shape and size. I hope you understood very well. Okay. Okay. Yes, God. This is why the bridges are declared unsafe after the long time of their use. Yeah, even bridge has what? Bridge is also elastic. Vehicle are going, coming, going, coming. They are applying the following force. At the same time, bridge is also applying restoring force, and this is repetition. At a point, at a time that bridge loses its configuration, so it is advised that a bridge after a long time bridge is unsafety. Bridge is unsafety. So that is why the bridges are declared unsafe after a long time of their use This was an example. Bridge is an example. I think it is the best example of elastic fatigue. Elastic fatigue. Now next concept. Now next. Next is elastic potential energy store. In the stretched wire or in a rod. What would be elastic potential energy in a wire when wire is stretched? We know when wire will be stretched or rod, then what will happen? That wire or string will gain potential energy so that it can regain its original shape. Am I correct? Yeah, it was a basic point. Equation, we are going to find equation so that questions can be solved based on this concept. So what would be that equation? This is important for this topic. This elastic, I'm not saying electric potential energy, I'm saying elastic potential energy, or you can write it in short as EPE. If you are in this context, then you understand, yes, this is nothing but elastic potential energy. If you are in the context of electricity, electrostatic, then in that context we understand that we have electrostatic potential energy, or you can say electric potential energy. But 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 we need to stay in our context. So strain, who will provide stress or strain? Strain will have potential energy, but how did it gain? How did object gain potential energy? Your answer is due to stress. Due to stress. So strain energy stored in in the in the equivalent spring, in the equivalent spring. U is equal to, finally this is equal to 1 upon 2 kx square. Remember, f is equal to minus kx is a formula of a spring, but over here this u is representing what? Potential energy. Potential energy, which is equal to half kx square. Half kx square. This thing we have to bring logically. Okay, logically. Where x is nothing but x is a f l upon ay. Remember, f upon a is a stress, but change in length upon modulus, Young's modulus of elasticity. Y is Young modulus of elasticity, and L is a change in length. Just substitute this value in this equation. Gradually you will get your equation for this topic. And value of k is nothing but a y upon a. A y upon a. Let me draw a figure. This is figure. You can see, if you are taking rod, so this is our change in length and force is downward. This is our deforming force. This is also deforming, and upward force will be restoring force. So A is what? Area. Y is nothing but Young's modulus, and L is the length of this rod. Clear? And it's a string. This was rod. So here x is nothing but f upon area, which is a stress. F upon area. But change in length upon y it will give you value of Ax. To get this thing, we have F into L upon A into Young's modulus. And Young's modulus is nothing but this provides stress upon strain. Stress upon strain. So finally we can put this value in this equation. Then see what will happen. 1 by 2 Ay L F L upon Ay raised to power 2 raised to power 2. This can be simplified further, then it will provide us F square L square upon A square Y square Y square. This equation that came can be rearranged. Let's see how. Here U is becoming 1 by 2 F square upon A square multiple change in length A upon Y. Just we rearrange it, nothing else. 1 by 2 is as it, and F square upon A square, we brought this thing over here, multiple, then this L over here, and A by Y. Look carefully. This A and L is over here. F square. But what about one more L? A square Y as it. Okay. And we know that L is nothing but this is a volume of a rod. This L is nothing but volume of a rod, and F upon A is nothing but this is a stress. So finally you can say U is equal to 1 upon 2 stress raised to power 2 upon Y, and F upon A is nothing but this LA is nothing but volume of rod. And strain is what? Strain is equal to F upon AY. This is becoming volume. So finally you can say U is nothing but 1 upon 2 stress multiple strain multiple volume. Restoring force, change in length and change in volume upon 2 is equal to U. Half stress multiple strain multiple volume. Okay, I am leaving this till here. Now again let's repeat that graph which we were talking about in particular part, that was about curve of stress and strain. One more time we are going to explore it so that it can it can become more clear for us. Graph is something like this. 30% stress strain. This is going in this direction, this is in this direction. SY this is T, which is SU. One by one, each points, each terms, we will explain each terms related to this graph. This is a zero. Oh, okay. Oh. Try to understand. From here to till here, to this A point, this is constant. Remember, this is constant. From 0 to A, because it is just a line, not curve line. Not a curve line. Clear? Proportional limit. Proportional limit. Or you can say this is nothing but it is a proportional limit. Proportional limit. If you cross, if you go beyond A, what will happen? You will see that this is not flowing Hooke's law. This is not flowing Hooke's law. Because beyond this A, it is not straight. This is not straight. That's why. Or you can say it is not a constant. Constant gives us directly proportionality. Okay. So till A is our proportional limit, and it is providing from 0 to A is providing constant. And this B point is elastic limit. This is elastic limit. I have explained what is the elastic limit. This is a limit where we get maximum stress. Here is a maximum stress. You can see stress beyond this B till here. Maximum stress is a fixed, which is a constant. But strain is increasing. We will talk about. First of all, let's complete meaning of elastic limit. This is a limit where if we cross this limit, this point, then object becomes what? Object becomes plastic. Means that object will not be able to regain its configuration. This is what is the meaning of elastic limit, where if we cross this limit, then that object will become plastic. That object will behave like plastic behavior. But within elastic limit, this will provide behavior of elastic. But after this point, it will behave what? It will provide behavior of a plastic. Okay. B till this is C point. C point. This is nothing but this curved line is our plastic behavior. Plastic behavior. Behavior. Okay. Here beyond C, it is behaving you can say it is acting like a plastic behavior, and it's a truth. Means after this B, it's becoming plastic material. Okay, plastic material. Okay, try to see. This is making an angle. So this 1%, this gap, 1%. This is known as permanent set. Permanent set means our body becomes plastic for permanently, not for temporary. This is what is meaning of a permanent. Okay, permanent. But remember, from here to till here, this will be our permanent set. Okay, next. D is nothing but, ignore this right now. This E is our fracture point. Where body will break itself. Fracture point is where body will break itself. Okay. This was about those terms that are related to stress strain curve. Stress strain curve. See carefully. Now let's take a question. Now let's take a equation. Okay, enough. So what topics did we studied? What topics? We started from rigid body. Am I right? We started from rigid body. Rigid body. Then we saw deforming force, restoring force, deforming, restoring. Then elastic what I think came. Stress, types of stress, longitudinal stress. Then it has two types of stress, which is tensile, not tangential. Second, which was a compressive stress. Second type of stress was tangential. Then shear stress, volumetric stress. Then we entered into strain topic. Am I correct? Strain, change in length upon length. It provides a ratio and change, change in length or change in volume. Then we saw types of strain, which was longitudinal strain, tangential strain, uh, what strain or tangential strain. Yeah. Then we saw volumetric strain. Okay. After this, we saw Hooke's law. Hooke's law. From Hooke's law, we got what modulus of elasticity or coefficient of elasticity. Hooke's law was saying that according to me, the strain the stress produced in the body within an elastic limit is directly proportional to strain produced in the body. This was a statement of Hooke's. Then we saw yes, stress is directly proportional to strain. When we are removing directly proportionality, then equal is coming and A is coming. A is nothing but this is a coefficient of what? This is coefficient of stress. No, strain. Then we saw A is becoming 2, or you can say A is equal to stress upon strain. Stress upon strain. And this is what is known as a coefficient of elasticity. And we call it as a, we can call it as a what? Modulus of elasticity, which is represented by. Then we saw types of modulus of elasticity or coefficient of elasticity. So first was Young's modulus of elasticity, which is denoted by y, and y is equal to stress upon strain. Okay. It says that I am the ratio of stress upon strain. The same for E. Okay. Then after understanding Young's modulus, then we saw about Boolk's modulus. But remember, Young's modulus are for, this is valid for solids, not valid for liquids. Okay, fluids. But Boolk's modulus of elasticity is valid for solid as well as fluid. And B is denoted by K or B. Compressibility is nothing but this is a reciprocal of K or B. Okay. And B was saying that B is equal to strain, volume strain, I think longitudinal strain or lateral strain, longitudinal strain upon sharing strain. I am forgetting, but I think it should be this. After Boolk's modulus of elasticity, then we saw modulus of rigidity. Modulus of rigidity, which is denoted by this n. And it was saying something else. Then we saw Poisson's ratio, which is denoted by like this. Poisson's ratio. Okay. After this, rigid body. Okay. After this Poisson ratio, then curve of stress and strain. Terms are constant, elastic limit, yield point, plastic behavior, elastic behavior, range, elastic range, plastic range, permanent state, breaking point, breaking stress, breaking strain. Then we saw uh, yeah, elastic after effect, which was nothing but it was saying the delay. This is defined as the delay in the its regaining of configuration of the body on removal. The foreign force is known as elastic after effect, and we saw examples. Examples. A steel has more elastic. A steel has a large elastic after effect because that steel takes too much time to gain its origination. But when it comes to rubber or flexible solid object, then it is able to regain its original shape within a short time, or you can say it takes a very less time as compared to steel. That's why it is said that flexible body has a less less elastic after effect. After this we saw elastic fatigue. Elastic fatigue, it say that I am nothing but elastic fatigue means repetition. A body will lose a body will lose what its configuration, or you can say it body will not be able to, eventually body is able to regain its configuration after removing uh, what deforming force. But after a long time, when deforming deforming forces continue, restoring forces also continue. After a long time we observe that yes, body is losing its configuration. Its configuration, it happens due to repetition of it happens due to repetition of deforming force and restoring force. This is what is our elastic fatigue. Shockers, springs are examples of elastic fatigue. Okay. Okay. Yeah. And this is what is the reason behind saying after a long time breeze is considered as unsafety. Unsafety. Why? Why? Because they lose their configuration. That's why. That's why it is said that breeze is unsafety. Breeze is unsafety. Okay. Breeze is unsafety.